Okay, now before choosing a specific type of compressor, consideration must be given to a number of important factors. These include discharge pressure, capacity, power supply characteristics, availability and cost of cooling water, space required for the compressor, compressor weight, type and size of foundation, type of process control, which is very important, and maintenance costs, just to name a few. The initial choice is between the two basic types, which are, if you recall, positive displacement and dynamic. Once this decision is made, you can make a further study of the characteristics of various compressor types to see which one will be best for your application. Keep in mind that the selection of a compressor is an engineering decision in which every factor should be considered. Remember, the average life of a compressor is usually 30 years, so every decision made that affects the operating cost will be in effect for a long time. For a quick review of compressor selection possibilities, it is best to consider only horsepower and pressure. The upper limits for each type of compressor are summarized in the following table. Here you can see the approximate application ranges for reciprocating, rotary, centrifugal, and axial flow compressors. Of course, these maximums are subject to certain limitations imposed by other factors and, under certain conditions, can be exceeded. Let's focus on the differences between reciprocating and centrifugal compressors. Reciprocating compressors, as we have seen in a previous video, deliver a constant volume flow and are insensitive to gas characteristics and system resistance changes. On the other hand, centrifugal compressors deliver a varying volume flow. Actually, the fundamental characteristic of these machines is decreasing discharge pressure with increasing flow. These compressors are highly sensitive to gas characteristics and to system resistance. So, if, for example, you need to purchase a compressor for your plant air or instrument air system, it is better and recommended to go for a reciprocating compressor rather than a centrifugal compressor. Since your plant or instrument air demand will require a constant flow regardless of system resistance, and this can only be achieved with a positive displacement compressor. Now, the operation of a reciprocating or a centrifugal compressor in a process system is so important that we have built a separate section to discuss the differences and similarities between these two types of compressors. This dedicated section is one of the most important sections of the course in understanding the principle of operation of reciprocating compressors. So, we recommend you to watch it carefully. And feel free to ask us for help in the Q&A section if needed. Also, prior to watching this section, we strongly encourage you to have a look first at our bestseller course dedicated to centrifugal compressors, principles, operation and design. And don't forget to ask us for a coupon code to enroll in with a discount. In this video, we will focus our attention on air compressors and the considerations that apply to them for the selection process. These considerations include many factors. First, we list them, then we will discuss each one of them in detail. These factors are load factor, multi-staging, floor space, foundation needs, capacity control, oil-free air, and cost of air. For the first factor, Load factor is a consideration in the smaller installations where only one or two compressors are to be installed. Load factor is simply the ratio of actual compressed gas output while the unit is operating to the rated full load output during the same period. It should never be 100%. The best practice is to select an installation with a load factor between 50% to 80%, dependent upon the size, type, and number of units involved. Proper use of load factor results in more uniform pressure even during peak demand periods, a cooling off period which is extremely desirable for air-cooled units, less maintenance, and spare capacity, or in other words, the ability to increase use of air without immediately increasing the plant size. Load factor is very important with air-cooled machines, where sustained full load operation results in an early build-up of deposit on valves and other parts of the compressor, thereby adding to maintenance. Intermittent operation is always recommended for these units. The degree depends upon the size and operating pressure. The standard or rule for multi-staging is that any air-cooled reciprocating compressor for 80 psi or higher pressure should have 2 or more stages of compression. A two-stage unit for 100 psi, as depicted here, will run 100 degrees Fahrenheit cooler than a single-stage unit, therefore reducing deposit formation and the need for valve cleaning. Two-stage compression of air to 100 psi also saves 10 to 15% in power over single-stage compression. Heavy-duty water-cooled units for the same service are more economical to operate than the air-cooled units and normally run at lower speed and temperature. Therefore, maintenance will consistently be less. For this reason, they are universally two-staged for 100 psi air service above 125 brake horsepower. The next consideration is floor space. Floor space and its shape will at times influence selection. The opportunity for selection will be broadened if the exact dimensions of the space available are given to all manufacturers. Design adjustments or alternate arrangements are often available. Here, just keep in mind that in general, foundation needs for reciprocating compressors will almost always be greater than for centrifugal rotating compression machines like centrifugal compressors. For the important factor related to capacity control, here variation in demand for gas must be considered. It usually ranges from full compressor capacity to zero. The different types have widely varying ability to handle this range, some being much more economical at part load than others. In this regard, reciprocating compressors are particularly favored in this area. Capacity control of reciprocating compressors can be achieved using various techniques as listed here. These techniques will be discussed in detail in the capacity control section. The next factor is oil-free air. Here, any requirement for air completely free of oil will rule out any design that operate with oil. This is a criteria to pay attention to, especially if your compressor will be used for instrument air supply. Finally, the last factor, which is the cost of air. Keep in mind that compressed air is never free. It costs a considerable sum, and the selection of a compressor should always consider this factor, in particular for heavy-duty service. Here, two facts should be mentioned. First, power cost is by far the largest item in overall air cost. And second, power cost over the service life may be many times the first cost of any compressor. The process gas compressor is called upon to handle many diverse types of gas. It is practically never spared. 24 hours a day, 7 days per week operation is the general rule. Here, continuity of operation is highly important. In this video, we will focus our attention on the considerations that apply to process compressors for their selection. These considerations include many factors. First, we list them, then we will see each one of them in details. Among these considerations, we have gas characteristics, process conditions, driver, oil contamination, foundation, multi-service units, first cost, and power cost, just to name a few. For the first factor, gas composition and characteristics can have a decided influence on compressor type. A low gas inlet density, for example, will usually affect the centrifugal compressor to a greater degree than it will affect the positive displacement machine. A centrifugal compressor handling low-density gas will require many more stages than when handling a high molecular weight or specific volume inlet gas. Keep in mind that in this regard, reciprocating compressors are not affected by the gas molecular weight, specific volume, or inlet density. For the second factor, in any compression problem for a given compression ratio, the flow rate to be handled establishes the physical size of the equipment under consideration. For example, if 80,000 cubic feet per minute of gas must be compressed at near atmospheric suction conditions, a centrifugal compressor would almost certainly be used for the lower stages of compression. In centrifugal compressors, if suction pressure is raised, the discharge pressure will exceed the design point. The horsepower will increase, and excess pressure may have to be throttled down. Now, if the suction pressure is lowered, the centrifugal compressor will not compress to the desired discharge pressure. Therefore, it is most important that the suction and discharge pressure, their variation and resulting influences, be accurately evaluated. Low compression ratios with reasonable capacities favor the centrifugal compressor. High compression ratios and higher pressures favor the reciprocating compressor. Here, don't try to attempt to define the borderline in pressure between reciprocating and centrifugal compressors. Why is that? Because there are too many other factors to be considered. In some multi-stage process compressors, as the example you can see here, the interstage pressure is set by the process. This may be for washing out undesirable elements, adding gas, or carrying out chemical reactions that change the nature of the gas between stages. For this reason, it is important that such interstage pressure restrictions be considered, including the pressure drop involved. For the factor relative to driver, in general, if choice of driver is dictated by the available source of power, the heat balance, or any other factors in the plant, the compressor that best fits the driver should receive first consideration. In other words, and to put it simply, the centrifugal compressor always receives first consideration if the driver must be a turbine. The reciprocating compressor should probably always receive first consideration if the driver is to be an electric motor. This is because the majority of motor-driven centrifugal compressors require a speed-increasing gear, which increases the investment and maintenance cost by a considerable amount. Oil contamination can have a bearing on compressor type selected. The degree of importance attributed to oil contamination will also influence decisions. Partially lubricated or non-lubricated reciprocating compressor designs may be more suitable than centrifugal compressors. For foundation and floor space, soil and foundation conditions must be considered in compressor selection. In a few instances, this dictates the type of machine. A centrifugal compressor operates without producing unbalanced forces. The foundation will need only to support the dead weight load with adequate stiffness to maintain alignment. The type of reciprocating compressor most widely applied today in chemical and process plants is designed specifically for a minimum of unbalanced forces. In general, a foundation that will support the dead weight load of the compressor and maintain alignment of compressor and driver will have adequate mass to absorb the small unbalanced forces that may be present. The centrifugal machine will usually be favored from both the foundation and floor space standpoint if this is the only consideration. For the next factor, for sound economic reasons, process plants have been installing fewer compressors to do a given job, using larger sizes and no spares. When the process requires handling of many streams, which is a common occurrence in some types of plants, compressors can be so configured that several streams may be handled by a single driver. It is not often that more than two services are handled in a combination of centrifugal casings having a common driver, because there are problems of capacity and pressure control as well as other factors. However, with reciprocating compressors, greater flexibility is possible in the number and size of streams that can be handled on a single driver. Desired capacity control is usually more easily attained as well, and this will be discussed in detail further ahead. Now, just to share this information with you, in my industrial experience, as many as 5 separate streams have been handled on a large reciprocating compressor, and this is of course not possible with centrifugal compressors. For the first cost, there is no formula for establishing the relative cost of the centrifugal versus the reciprocating compressor. If volume, pressure, and all other factors are the same, then gas-specific gravity can influence the cost of the centrifugal compressor, but keep in mind it will have little effect on the reciprocating compressor. Finally, the power cost throughout the service life of a compressor is many times the first cost. While it is possible that the more efficient machine may be higher in original installed cost, the power savings over a period of years will usually quickly pay off the differential and return a profit for the remaining life. Except at very low ratios of compression, the centrifugal compressor is inherently less efficient than the reciprocating compressor. However, very large volumes, low ratios of compression, and low final pressures favor the centrifugal compressor. Actually, as an example, no one today in the industry would think of using the reciprocating compressor for blast furnace blowers. Conversely, higher ratio of compression and higher terminal pressures favor the reciprocating compressor in other services.